Hello. Is my screen visible to all of you? I hope the screen is visible to everyone. Just write it in the chat if the slides are visible. Okay, thank you. Okay, so we'll continue with the topic about the transport layer in computer networks and internet protocol. In this lecture, we will broadly cover how the TCP protocol is implemented in the transport layer. And then further, we will also see how the UDP, what is UDP protocol? As we said, transport protocol, transport TCP protocol is a very reliable protocol. However, there are certain conditions when the reliability is not needed, and for that purpose, end-to-end delivery is needed for at a faster pace. So for that purpose, we rely over the UDP protocol. So in this lecture, we will cover those aspects. Firstly, we will see the remaining part of the TCP. Okay, let's wait for 2 more minutes and let everyone join. Okay, so first let us discuss the previous assignment. This just a minute. So these are the few questions of the assignment. Wait, I'm not. So first one is, which of the following statements is or are correct concerning to the TCP acknowledgement number? So these are few of the topics that we have already covered in the previous lecture, and we are right now. This was the assignment that was circulated amongst all of you, and we are discussing this assignment with the solutions. So which of the following statements are correct uh, regarding concerning the TCP acknowledgement number? So it is a 16-bit number. It contains the sequence number of the previous bytes the receiver has received. So I would like everyone please answer to the question in the chat. Okay, so the answer is D. That is, none of them are correct. So TCP acknowledgement and the sending size is both of them are 32-bit in length. That is why the sequence number is 32-bit in length. That is a sequence number, and it contains the sequence number of the next byte that the receiver expects to receive on a connection. It is not the sequence number of the this as mentioned of the previous bytes, but it is the sequence number of the next byte which the receiver is wanting for the next round from the sender side. Okay, so the next question is, if maximum network layer payload is 2 KB, what is the maximum TCP payload size? 2 kilobyte. I would like everyone to answer the question that if the maximum network layer payload size is 2 kilobyte, what is the maximum TCP payload size? Okay, so the answer is B, that is 2028 byte. Uh, it is because the TCP header can range from 20 to 60 bytes. So the maximum TCP payload would be maximum network payload minus minimum header size. So maximum network payload is 2 kilobyte, that is 2048 byte, minus 20 bytes, that is the minimum TCP header, that gives out to be 2028 byte. Okay, so the next question is, packets of the same session may be routed through different paths in both TCP and UDP, neither TCP nor UDP, TCP but not UDP, UDP but not TCP. Question number 3, everyone please respond. Packets of the same session may be routed through different paths in both TCP and UDP. Okay. So TCP and UDP are transport layer protocols. The packets of the same session may be routed through different routes. So which of the following system calls result in sending of SYN packets? Socket, listen, bind, or connect? SYN, if you remember, is the synchronization packets for synchronization. So during which system calls those packets are sent? The correct answer is D. While the connect, following the connect system calls, in case of TCP socket, connect system call causes an attempt to establish a new TCP connection. When the connection is established or when connect is called by a client, a three-way handshake happens to establish a connection in TCP. So first is that the client requests a connection by sending a synchronization message to server. Then the server acknowledges this request by sending a sync acknowledgement back to the client, and then the client responds with an acknowledgement and the connection is established. Which of the following statements is or are true for the transport layer? Transport layer protocol should be stateful. Second, it uses FTP protocols for ensuring flow of control. So the correct answer is A, that only one is correct. That means the transport layer needs to remember the state of the pipe so that appropriate actions can be taken. So we need a stateful protocol for the transport layer. Moreover, ARQ protocols are used for ensuring flow control, not FTP protocols are used for ensuring flow control. Next question. Which of the following is helpful to avoid TCP SYN flood attack? Use of cryptographic function to generate sequence number for TCP connection is helpful to avoid what? So the correct answer is C, that is cryptographic functions generate sequence numbers that help in avoiding the TCP SYN flood attack. What is or are the parameters responsible for restricting TCP segment size? IP address, IP payload, maximum transmission unit of the link, or acknowledgement number field size. The correct answer is B and C, that is IP payload and acknowledgement maximum transmission unit of the link. The TCP segment size is restricted by these two parameters. Then IP payload 65515 bytes and MTU of that link. The next question is for effective collision congestion avoidance, the sending rate of the network should be minimum of the network rate and the receiver rate. Is the above statement true or false? Yeah, so correct answer is true. That is, the sending rate should be based on what the underlying network can support. So should be kept minimum of network rate or receiver rate for effective congestion avoidance. So TCP supports broadcasting. The above statement is true or false. That means correct or wrong. So the TCP cannot broadcast, it support point to point communication only. So this statement is wrong. Uh, okay. Okay, so this you just put up again. You have written DJ that this was, yeah. I mean, this is wrongly answered by NPTEL. The statement is wrong. So you just put up in that discussion forum or mail your TAs. That means the normal TAs for NPTEL course, and they will give you the answer to that query, and they will always rectify it. What is the default port number for establishing HTTPD connection, Apache server connection? So I have no clue about the ID. You just check with the NPTEL TAs that have been allotted for the course, for the core marking scheme, because we have no access to the marking scheme. So HTTPD is established through port 80. That means none of the above. Okay, so we're done with this assignment. So we'll discuss the other assignment later on. So for now, we will be continuing with the today's lecture that talks about the TCP congestion control firstly, and then we'll talk about the UDP. So TCP congestion control, this thing we have already covered. So broad, giving a broader idea that based on the implementation of AIMD using a window and with a packet loss as the binary signal. So TCP maintains a congestion window, that means CWND, that is equals to number of bytes the sender may have in the network at any time, so as to control the congestion or to avoid the congestion. So that what is we need to study some of the terminologies. One is the sending rate, another is the sending window. The sending rate is the congestion window upon RTT. That means sending rate. That means at what rate the sender is able to send a packet or some packets from the sender at the receiver end. So that is equivalent to the congestion window divided by the round trip time. Then it's the sender window, which is equivalent to minimum of the congestion window and the receiver window. So, receiver window is the window size of the window advertised at the receiver end. So, how the congestion collapse occurred from 1986? So, in 1986, there was a growing popularity of internet, which led to the first occurrence of congestion collapse, which is a prolonged period during the good put dropped. Where the good put was dropped, but however, this congestion was not very extreme as we face these days. However, that was the first collapse scenario that we faced. So early TCP congestion control algorithm was effort by Van Jacobson, and the challenge that was proposed by Van Jacobson in 1988. So the challenge for Jacobson. Wait. So the challenge for Jacobson was that to implement congestion control without making much change in the protocol and made it instantly deployable. Just a minute. So the challenge was that to implement the congestion control without making any much changes in the protocol and made it instantly deployable. So the packet loss is how to check that there is a congestion in the network. So for that purpose, packet loss is a suitable signal for checking out for congestion. So it uses timeout to detect the packet loss. For a certain timeout, if the packet is not received at the receiver end, however, it has been sent out from the sender end. So at that time, a timeout occurs, and that signifies that the packet is lost on the way. So, accordingly, we need to tune the congestion window based on the observation from the packet loss, like at what point the packet was lost and after how much duration that packet was lost, etc. So one of the most interesting ideas how to adjust that congestion window based on the AIMD, and for that we use the acknowledgement for clocking. So here you can see, firstly the burst of packets are sent on a fast link. Then the burst queues at router and drains onto the slow link. So, firstly, and then the receivers acknowledge the packets at the slow ring rate, and then the acknowledge preserve slow link timing at the sender end. So, acknowledgement return to the sender at about the rate that packets be sent over the slowest link in the path. So, it triggers the congestion window adjustment based on the rate at which acknowledgements are received. So one of the solution is that to increase the rate exponentially at the beginning. That means a very slow start. That AIMD rule will take a very long time to reach a good operating point on the fast network if the congestion window is started from a small point. Because in AIMD, either we do the additive increase or the multiple increase. So initially when we do the additive increase, that means if there is only one MB of window, then there is additionally only one increment in that window size when we do the additive increase. So that will take a very long time to reach at the operating point of the fast networks. if that congestion window is started at the very small point. So for that purpose, for example, say a 10 Mbps link with a 10 millisecond RTT is there. So the appropriate congestion window is the bandwidth delay product, that is 1 Mbit. So 1250 bit byte packets are equivalent to 100 packets to reach the BDP. So if the congestion window starts at one packet and it is increased one packet at every RTT, then 100 RTTs are required for 10 seconds before the connection reaches to a moderate rate. So that is a huge time and is a very slow rate. So for that purpose, we need to increase the rate exponentially at the beginning. So the slow start, it means that exponential increase of the rate to avoid slow conversions. So the rate is not slow at all. Here, the congestion window is doubled at every RTT. So for example, if the congestion window is starting from 1, then it jumps to 2, then to 4, then to 8, then to 16, and so on. So that in that way, there is an exponential increase of the rate, and it avoids the slow conversion of the algorithm. As you can see here, every acknowledgement allows two more segments to be sent. Initially, the congestion window is 1, as can be seen in the figure. I hope everyone is clear till now. Here, the congestion window is 1, then it goes for 1 RTT, and then the congestion window converges to 2. Then it simultaneously sends 2 packets. Then it receives the acknowledgement for the 2 packets, and the congestion window reaches to 4. Then it sends 4 packet and then receives the acknowledgement for the corresponding 4 packets, and then the congestion window leads to 8. So for each segment that is acknowledged before the retransmission timer goes off, the sender adds one segment's worth of bytes to the congestion window. So it receives one, add one, receives one, adds one. So in this manner, TCP slow starts work with the exponential increase. So slow start causes exponential growth. Eventually, it will send too many packets into the network too quickly. To keep slow start under control, the sender keeps a threshold for the connection called the slow start threshold. So initially that SS threshold is set to BDP, or that means it is arbitrarily high. That means BDP, the maximum bandwidth delay product which is available. At that point, the slow start threshold is fixed. That is the maximum that a flow can push to the network. That means a flow which is coming from the sender end and the flow which is received by the receiver end, that is the maximum flow which can be pushed through the network, is set as the slow start threshold. So the growth is done exponentially till the slow start threshold. In the meanwhile, whenever a packet is lost, is packet loss is detected by the RTO, then the SS threshold is set to be half of that congestion window. So whenever the SS threshold is crossed, TCP switches from slow start to the additive increase. It is usually implemented with a partial increase for every segment that is acknowledged, rather than increase of one segment per RTT. So the congestion window then is equivalent to the previous congestion window plus the MSS into MSS divided by the congestion window. That means the maximum segment size. MSS is the maximum segment size. A common approximation is to increase the congestion window for additive increase as follows. This is the data that we send 1 with the congestion window 1 received, and then it is added up to 2. Then we send the 2 packet, then receives back. Then it is congestion window is moved up to 3. Then we send 3 packets, and then they are received back, and the congestion window moved up to 4. So there are two ways to trigger a congestion notification in TCP. One way is the retransmission timeout, and another way is the duplicate acknowledgement. I hope it's clear to everyone till now. So RTO is a sure indication of congestion. However, it is very time consuming. Because there might be a case that the network keeps on waiting till the RTO and the packet is lost beforehand. So the bandwidth is getting wasted. So for that purpose, there is another way, that is duplicate acknowledgement, which receiver sends a duplicate acknowledgement when it receives out of order segment. So it is a loose way of indicating congestion. Here TCP arbitrarily assumes that 3 duplicate acknowledgements dupacs imply that a packet has been lost. That means it triggers congestion control mechanism. The identity of the lost packet can be inferred the very next packet, that means the very next packet in the sequence. It retransmits the lost packet and triggers congestion control algorithm. So it is a very loose way of indicating congestion. In that way, there are 3 duplicate acknowledgements that are sent from the receiver side. So if you receive 3 duplicate acknowledgements saying implying that the packet has been lost, it triggers the congestion control mechanism. So the identity of the lost packet inferred is the next packet in the loss. For example, wait. So as we can see here, fast retransmission method using 3 dupacs as a sign of congestion, that is called TCP TOHE. And in this moment, it starts with an exponential increase in a slow start manner and obtain a threshold 32 kb where the packet might get lost. After that, it adds up the additive increase method. So then again the packet is lost, then it drops and move the threshold to half, that is of the current slow start, that is equivalent to 20 kb. So then again it starts from a slow start, exponential increase, and then additive increase after the threshold is attained. So once 3 dupacs have been received, it retransmits the lost packet. That means the fast retransmission, which takes 1 RTT. So at that moment, it sets SS threshold as half of the current congestion window. Here the congestion window is set to 1 MSS. So now we see why the congestion window is set up to 1 MSS. It is done in the fast recovery mode. Once a congestion is detected through 3 dupacs, so do TCP really need the congestion window equals to 1? MMS, MSS, that means the DUPAC means that some segments are still flowing in the network, a signal for temporary congestion, but not a prolonged one. So immediately it transmits the lost segment, the transmitted additional segments based on the DUPACs received. That means it is the fast recovery. That is TCP Reno method. I think all of you are clear with these things in the lecture as well. I'm just giving a broader overview of what has been taught in the lectures. So fast recovery here, what it does is set the SS threshold to one half of the current congestion window that we always do. Then it retransmits the missing segment. Then it sets the congestion window equals to SS threshold plus 3. So each time another duplicate acknowledgement arrives, set congestion window equals to congestion window plus 1. Then sends a new data segment if allowed by the value of congestion window. Once it receives a new acknowledgement, an acknowledgement which acknowledges that all intermediate segments sent between the lost packet and the receipt of the first duplicate acknowledgement, it exits first recovery. This causes setting congestion window to SS threshold. That is SS thresh in step 1, and then continue with the linear increasing due to congestion avoiding algorithm. We show this in the case of example. Here you can see that this is the sender side and this is the receiver side. So the congestion window size is 1. It sends out 1 packet, receives the acknowledgement, sends another 2 packet, receives both the acknowledgement, then send another 4 packet. In the meanwhile, packet 5 gets lost. So there is no acknowledgement received for packet 5. However, for this congestion window 5, it sends packet 7, packet 8, packet 9, and packet 10. So for this purpose, we send first du duplicate acknowledgement. Then it sends second duplicate acknowledgement, then third duplicate acknowledgement, and then fifth duplicate acknowledgement. So this is how the packets are retransmitted with the duplicate acknowledgement till all the packets are received at the receiver end. Now we will discuss about the user datagram protocol. If anyone has doubt till here, you can ask. Then we will continue with the user datagram protocol. As you see that transport, that is TCP protocol, offers many of the services. That means connection establishment, reliable data delivery, flow and congestion control, order delivery, packet delivery, etc. However, in case of datagram delivery, that is a very unreliable mode of data transfer. So the features is that it provides performance, that means no data holding in buffer like TCP. So while implementing all the congestion control and the flow control and each and every connection establishment and the connection ending, so it might be the case that during that part the TCP uh, gets slow. So the data rate of data transfer or the data transmission is very slow and is unable to follow the data transfer protocol. So for that purpose, we require UDP for providing a better performance. Then another feature is that UDP is very short and sweet. It has no overhead and it is suitable for the short messages. So the uses of UDP is that it is a very simple protocol that is a wrapper on the top of IP layer, and it is a fast protocol that means no flow control, no congestion control needs to be done. So UDP is a connectionless and unreliable protocol. So here no connection establishment, no reliability or no acknowledgement is received from the server to the client side or the client to the server side. So the UDP header, we have already seen the TCP header. So here is the UDP header, which contains the source port, that is the port number of the source, then the destination port, then the length of the UDP header, then the checksum, and then the data. So what exactly is the checksum? So checksum is used at the UDP header end for checking if the message has been sent from the sender side to the receiver side correctly or not. That means the message is sent with an encryption and at the user receiver side it is decrypted from the receiver side. So what are the applications of the user datagram protocol? First application is the DNS, which is domain name server. So here, simple request response messaging system is faster than the TCP. So there is no need for this. There is no need for the reliable data communication. Next one is the boot p and the DHCP. That is for the network configuration. It is the short messaging helps faster configuration. That means the short messages are delivered and it helps in faster configuration at a faster rate. Then for TFTP file transfer, also lightweight file transfer protocol is needed to transfer small files. Then for SNMP, that means for network management, when there is congestion in the network, simple UDP protocol easily cuts through the congestion than the TCP. And then comes the quick protocol, which is the advanced transport protocol. Here UDP provides direct access to IP while TCP can't. So we'll discuss what exactly quick is. Quick is a quick UDP internet connection protocol, which is which means that the services which are being offered at the TCP layer protocol, those services are offered as an application side. So all the services that has been many of the services apart from the data sending which are implemented as a part of TCP are implemented as a part of application side during the quick protocol. So here Quick needs a zero RTT connection. That means Quick sends the incollate message of client hello from the client side to the server side. So whenever the in a Quick protocol it wants to send a message from the client to the server side, it encrypts that message with an encryption. So if there is no encryption available, then the receiver side will reject that message and then again ask the client side to resend the message. So again, the client side will resend the message with the complete client hello and with the encrypted request. After that, the client respond with the server hello and with the encrypted response. So every message has been sent from the client to the server, server to the client should be encrypted. So this handshaking is done in one RTT handshake. Then for the other case, when the message has been sent from the client side with the encryption, at that time the handshake is maintained with the zero final handshake. So here the advantage of the quick over the TCP is one more also, that in case of TCP, whenever the connection needs to be established, every time we need to do the three-way handshake method. However, in case of this quick protocol, if once the connection is established and a handshake is has been done, then there is no need for handshake for the further communication or data transfer. So when the first time all the messages are received with an encrypted request, that means it is being connected in zero RTT handshake. Then repeat handshake, that means the complete request from the client side is sent with an encrypted request. Then the server side rejects that request, and again the complete request has been sent from the client side, and finally the server side request receives accepts the request and responds with the acknowledgement. So that is the rejected zero RTT handshake when the handshake needs to be repeated. Further, we will be covering socket programming in today's lecture. If anyone has doubts till now, you can ask for it. I'll wait for 5 minutes. Okay, so we'll start with the socket programming. So in the case of socket programming, as we have already, what is exactly socket programming? We have already seen that we implement the transport layer protocol at the kernel end. So there is this physical layer and a part of data link layer which is implemented at the hardware level. Then there are major part of the data link layer, network layer and the transport layer is implemented at the kernel end or the kernel space. And then there are the applications which are running at the user space or the user end. So whenever a device A wants to connect to device B, so there can be multiple applications which are running on a single device. So for example, an HTTP application of browsing is running on device A with the TCP protocol. Then the file transfer from A to B is running with the TCP protocol, and the VoIP is using the UDP protocol from for communicating from A to B. So there can be multiple applications that are running. These are the applications which are running at device layers. And then there are multiple protocols with which the applications are running. And however, there is only single IP of that particular device. So each of the application finds a port or a process for it to communicate. Okay. So it also has a one port, it also has one port. So everything has one port for a different application. Then, however, if you want to communicate from one machine to another, that requires a single IP. For example, here the IP is 20.20.1111119 dot 05.180. Here the IP is 20.120.240. So via the means of individual IP, one is able to interact with the other machine. Okay. So what happens here is the two machines are interacting at the network layer using the IP address. So the details about the IP address we will be discussing in the subsequent lectures. So for each of the individual applications, the device A needs to connect to device B, and for that it needs to maintain a single pipe. Here this is pipe 1 for this application, then this is pipe 2 for another application, and this is pipe 3 for another application. So for each of the process to communicate with each other, an individual pipe is created among all these processes. So this is known as application multiplexing in TCP/IP. That a similar device runs with the multiple applications, and two devices are interacting with each other using more than one application with different protocols for each of the application. So a socket programming framework or API is a set of system calls to get the services from the TCP/IP protocol stack, that means the kernel level, and connect it from the user level. So the application level or the user space sends a command, and there are multiple system calls to get services from the TCP/IP protocols from the user at the kernel end. So how to connect the server with the client using the Socket programming. One, what is socket exactly? As we have studied, socket is a combination of port and an IP address. That means this is the port at which the application is running, and this is the IP address at which the machine is running. So, firstly, the server runs the command that is the system called socket, which maintains its IP address and the port of that particular application. Then it's initiate the bind request and the listen request, because the server is initially listening all the time for and is available for the connection to be established. Then at the client side, there is only the socket which identifies the port and the IP address of the client's end. And then further, there is this connect call which sends the for the connection from client at the server end. Then the server makes a connection using the accept system call. For then the client sends the message and the server receives the message. Then there is a possibility that the server sends the acknowledgement and the client receives the acknowledgement. Then both of them comes on a mutual consensus for closing the connection. This is how the client and server interaction is being able to communicate using the socket programming framework. So the internet is a trade-off between performance and reliability, as we have already studied. So some applications requires fine-grained performance, example multimedia applications, while other require reliability, example the file transfer. So the transport layer supports two services. One is the reliable, which is offered by the TCP, and another one is the unreliable, which is offered by the UDP. So there are two types of socket. One is the stream socket, that means the SOC stream, which is a reliable connection oriented TCP based socket. And another one is the datagram socket, which is the SOC dgram, which is unreliable connectionless UDP based socket. So this is how the socket API code is written. Int s equals to socket, in which the domain name is written, the type of the socket, whether it is TCP or the UDP, and the protocol. So it creates a socket domain. That means it is in the communication domain. Typically, it is used by AF INET. That means IPv4 protocol. That means what is the domain of the internet addresses or the domain in which the sockets can be formed. Then is the type, which is depicts the type of the socket. That means the SOC stream or the SOC dgram. Then it specifies the protocol, which is usually set to 0. So I think in the lectures they have asked you to explore why this is usually set to 0. Can any one of you answer me that question? Yes, your answer is right, that the default port can be given to the application. That is why the protocol is usually set to 0. Then it initializes the status. That means that is equal to the bind, which has sock ID and the adder port and the size, which reserves the port of the socket. So the sock ID is the socket identifier, which is always unique for the socket. Then the ADDR port is the structured sock adder in. That means the IP address and the port of the machine. that is usually set to in at ADDR any, which chooses a local address of the machine for that socket to be initialized. Then size is size of the sock adder structure. So the SIN family is the address family, that is AFINet for IPv4 protocol. Then SIN ADDR.S ADDR is the source address. That means it is usually sent to in ADDR any to choose the local address of that machine. And SIN port is the port number. We need to use H2Ns H2NS function to convert the port number from host byte order to network byte order when we are connecting from the user end to the uh, kernel end. So struct sock adder in server address or int port is set to 3028. Then the server addrs.syn family is set to AFINet. Then server addr.syn addr.s addr equals to addr any. That means that it's local address. Then s input is the H2 port, which means host byte order to network byte order is converted. So host byte order to network byte order, why? It is needed for the readability at the memory end. So those conversion can be the little Indian or the in the big Indian system. So little Indian is from right to left and big Indian is from left to right. For example, here you can see first the right bit is written, then corresponding to that, then left, then extreme left. And here the left bit is written first, then next, then towards the right. So this is the difference between the little endian system and the big endian system. Then it is the listen and the accept socket connection. What is done in the listen and accept connection? So here, this is the code written, that is struct sock adder in client address semicolon listen sock ft comma 5. So sock ft is the identifier given to the individual socket which is being established. Then 5 means that that particular socket is able to take up or connect up to 5 clients. So client is given, that is size of the client address. Then new sock ft is created, which means accept the sock ft and structure of that sock ft and the client address and the client length. So that means that socket and client has been accepted and build a connection. So there can be active open and passive open, two types of communication. In the passive open, the server needs to announce its address and remains in the open state and waits for the incoming connection. That is the passive open. And the active open is where the client only opens a connection when there is a need for the data transfer. That is the active open. So connection is here, the connection is initiated by the client only. So data transfers through sockets have been done in two modes, that is sock stream and sock dgram. Then sock stream is written in this mode, that is read new sock ft buffer space and 255, then write new sock ft that then the write message needs to be written and then the length of that message is 18. And for sock dgram, it mentioned receive from sock comma buff, then 1024, then 0, then struct of that sock address and from length. And then send to sock, get your message, the length of that message, and the struct of the sock address from where to listen and from length. I hope the socket programming is clear till now to everyone. Mm. So there might be a case of concurrent servers. That means there are multiple clients which are trying to connect to that server at the similar go. So for that case, we need to extend the server socket for multiple connection. So how the server process or the socket can be extended for multiple connection. So for that purpose, we use the system call which is known as fork. That fork system calls recreates multiple another process which is known as the another server process which is the child socket. Then these child socket communicate for the different individual processes. If the multiple clients wants to develop create a connection, for example, if there is one client which is already connected, then it is a fork connection with child one. Then there comes another child which needs a connection. Then again a fork connection is developed with another sock ID and another child. Then again another third client comes that develops again a fork child and the communicates with it. So what is iterative server? Here it listens that makes this socket ready to accept connection request. So if listen parent ft comma 5, that means it allows 5 requests to queue up. Then the main loop wait for a connection request, echo input line, and then close the connection. So it receives the client request and see the size of the client address. So while one, it accepts for wait for a connection request when there is a connection developed. Then it accepts the child request and then uh, do the further processing. This is a iterative server with only single process, a single request to be dealt with once at a time. So, however, how this iterative server works, the listen call sets a flag that the socket is in the listening state and then set the maximum number of backlog connections. The accept calls blocks a listening socket until a new connection comes in the connection queue and it is accepted. Once the new connection is accepted, a new socket file descriptor, say conft, is returned, which is used to read and write data to the connected socket. All other connections which come in this duration are blocked in the connection queue. Once the handling of the current connected socket is done, the next accept call accepts the next incoming connection from the connection queue, if any, or blocks the listening socket until the next connection arrives. This is how iterative server works. However, we need to extend that iterative server to the concurrent server. As we said, multiple clients want to connect to that server and the same go. So here, parallel processing of each incoming socket so that the accept call is executed more frequently and parallelly. Here first, through an accept call, new soc-ft is created. So if there is a new soc-ft is created, having a successfully accepted a client connection, the server now forks. If fork, that means it creates a child process. So that if the fork call is called, then it returns two types of variables. One is 0, that means the connection is established, and another one is the uh, this the client ID. So if the connection is established, then it will return 0. That means this child process will now communicate with the client through the send and receive system calls. So then when the process is done, then it close the soc-ft. Here it close the old socket, since all communication will be through the new socket. So we initiate this buffer, copy the message to it, and send the message to the client. So here it copy the message. We again initiate the buffer and receive the message from the client. So this fork every time, if it receives a 0 variable, that means a new child process is created and the server can communicate with the client. And if the fork call returns a client ID, that means this is the client ID which has been returned to the server for the connection. So this is the example of peer-to-peer chat application that this Alice send a message to Bob and Jane sends a message to Bob, and then Alice also sends a message to Bob, and then uh, Bob replies to Alice, and then uh, Alice replies to Jane. In peer-to-peer chat application, no central server is there to control the chat message delivery, and every user runs its own chat server. Note that Unix maintains every connection or socket as a file descriptor. You're also reading data from std input, that is the standard input file descriptor. Here the keyboard is mentioned, referred to that. Message communication is asynchronous. You can receive a message while typing. There is a select system calls which selects from multiple file descriptors that add the concurrent way to handle multiple file descriptors simultaneously, even from a single process or thread. So what happens in an iterative server implementation that I have done earlier? First is the accept, where call is blocked until you have completed the read and write calls. What if you do multiple read and write activities after accepting an incoming connection? So all other connections are blocked and waiting in the connection queue, and may get starved. So select is the way to break this blocking. So advantage is that you do not need to create multiple child processes now, and no need to worry about the zombies. So this works as a multiplexer where various file descriptors arrive with the read and write request, and then there is the signal, and it selects one file descriptor and responds to that, then another file descriptor, and so on. And then there is a timeout if there is no query addressed and the file descriptors are ended. This is how the select call works. It includes highest number file descriptor in any of the three sets plus one. That means if there are total three file descriptors, then it will set to 4. Then this is the read file descriptor. This is the write file descriptor. This is the exception handling file descriptor. And this is the timeout interval. So read file descriptor will be watched to see if characters become available for reading. Write file descriptor will be watched to see if the space is available for write, and accept FDS will be watched for exceptional conditions. Timeout is the interval that select should block, waiting for a file descriptor to become ready. The select call will block until either a file descriptor become ready, or the call is interrupted by a signal handler, or the timeout is expired. So this is how the file descriptor is passed in the select call. This is the select call. Here this is read set, this is null. A file descriptor is called. So how this select works? It loops over the file descriptor. For every file descriptor FT, it calls the FT's poll method, which will add the caller to that FT's wait queue and returns which events, readable, writable, exception currently apply to that FT. If any file descriptor matches the condition that user was looking for, select will simply return immediately after updating the appropriate file descriptor sets that the user passed. If not, however, select will go to sleep for up to maximum timeout the user specified. If during that interval an interesting event happens to any file, that file descriptor that select is waiting on, that file descriptor will notify its wait queue. This will cause the thread sleeping inside select to wake up. Select returns value that is -1 means an error was encountered. You should do something about it. I just printed the error. 0 means the call timeout without any event ready for the sockets monitored. And greater than 0 is the number of sockets that have events pending. That means read, write, and exception. Thank you. If anyone have any questions, you can ask. We will proceed to the assignment corresponding to this lecture. So let us now discuss these questions. So which one of the following is true? UDP uses congestion control. UDP uses both flow control and congestion control. UDP uses flow control. UDP doesn't have any flow control or congestion control. Everyone, please respond. The answer is D, that UDP doesn't have any flow control or congestion control, whereas TCP does. Sock stream represent UDP based datagram socket, TCP based stream socket, or quick based stream socket, or none of the above. Hmm. Everyone, please answer. Okay, so correct answer is B. That means TCP based stream socket. Third question is that FD0 is used for test to see if a file descriptor is a part of the set. Initialize the file descriptor set, FD set. That means a bitmap for fixed size. Set a file descriptor as a part of FD set or none. So the answer here is B, that it initializes the file descriptor set, FD set. So now, which of the following statement is true for the slow start? That means it leads to a slow convergence of the congestion window. The rate of increase of the congestion window is very slow. It increases the congestion window exponentially to reach faster convergence, or it slows down the three-way handshaking process. Okay, so the correct answer is the rate of increase of congestion window is very slow. Another question is that sender window in TCP can be given as sender window equals to maximum of congestion window or receiver window. Sender window is equals to the congestion window. Sender window is equals to the receiver window, or sender window is the minimum of congestion window and the receiver window. The sender window is the minimum of congestion window and the receiver window. Okay, so socket address is IPv4 address translated to IPv6 address, combination of IP address and the port address, combination of MAC address and the domain address, and application layer address. The socket address is the combination of IP address and the port address. Which of the following uses UDP? DNS, POP, HTTP, and FTP. So the correct answer is A, that DNS uses UDP for the data transfer, as it needs only the data needs to be pushed, but it doesn't need the reliable sending of the data as in case of the TCP. Okay. So next question is, when you create a socket as S equals to socket domain type protocol, why do you set the value of the protocol parameter to 0? As I think someone has already answered to this question. So the answer here is A, that the system selects the default protocol number for the domain and the socket type requested. Not the port number, sorry. Initially somebody replied the port number, but it is for the default protocol number for the domain and the socket type. So another question is, select system call returns 0 when means an error was encountered. This means that call timeout without the event, an event was ready for socket monitored, or 0 is the number of sockets that have events pending, or OS kills the process. Yeah, so it means that an error was in, sorry, this means that the call timeout without any event ready for the socket to be monitored. So last question is, in TCP congestion control mechanism is triggered once A. One duplicate acknowledgement is received after retransmission timeout, or three duplicate acknowledgement is received, or no duplicate acknowledgement is received. That the answer is B or C, either at the retransmission timeout or three duplicate acknowledgement is received. So that's completed our assignment. Anyone having any queries till now? We still have 10 minutes left. If anyone is having any query, you can ask. Mm. Okay, so if you have no queries, then we should end the meeting. You can leave the chat.